Okay, so this is chapter 4 and this is lesson 1. And in chapter 4 we're going to talk about reactions in aqueous solutions. What that means is we're going to focus on reactions in water, which is the most common universal solvent. It is essential for life chemistry, biochemistry, for example, cellular metabolism, and inorganic chemistry, like rusting. And we're also going to talk about acids, bases, and salts. So the first thing that we are going to do is define some keywords. Solution. This is a homogeneous mixture of two or more substances. The solvent, that is the substance doing the dissolving, and it's usually present in the larger quantity. And then we have the solvent, that is the substance being dissolved, and it's usually present in the smaller quantity. And then we have concentration. And that is a quantity of solute dissolved in a given quantity of solvent. And you're already familiar with this because it is expressed in molarity, which is capital M. So now we have to define molarity, and that is the concentration of a solution expressed in moles of solute per liter of solution. And you're familiar with this formula because we've used it in Regents chemistry. So it's big M and moles over liters. So here it says calculate the molarity of a solution made by dissolving 0.0575 moles of NH4Cl in 400 mils of water. So molarity equals moles over liters. And I think you all know that 400 milliliters is 0.4 liters. So this becomes very easy. And when we do the math, we get 0.144 molar NH4Cl. And that is our answer. Okay. Let's go through a couple of practice problems with basic molarity. In this example, it says calculate the molarity of a solution made by dissolving 9.93 grams of sodium sulfate in enough water to form 650 milliliters. And they gave us the molecular weight of the sodium sulfate as 142. So starting with our grams, we have 9.93 grams of Na2SO4, and we know that 1 mole is equal to 142 grams. Our grams are going to cancel, and that's going to give us 0.0699 moles. And we know that molarity is moles over liters, so I'm going to take 650 mils, and that's 0.650 liters. And I'm going to get 0.108 molar. Na2SO4. Okay. In this example, it says calculate the number of moles of HNO3 in 2 liters of a 0.2 molar HNO3 solution. So in this one, I'm just going to do some quick dimensional analysis. We know that we're trying to find moles. We know that we have 2 liters. And we also know that we have a 2 molar solution, which is really 0.2 moles per 1 liter. So I'm going to start with my 2 liters, 2.0 liters, because I know that this is 0.200 moles per 1 liter. That's your HNO3. Right? So now my liters cancel, and it's really easy because it's just 2 times 0.2, which is going to give me 0.4 moles of the HNO3. And the next one, what volume? So now we're looking for liters of a 0.3 molar solution of HNO3. Remember, when you see molar, I want you to be thinking 0.3 moles per 1 liter is required to supply 2 moles of HNO3. So we're going to start with what we're given, which is the 2 moles of HNO3. And you know the molarity is 0.3 moles, so 0.3 moles per 1 liter. And our moles cancel. So 2 divided by 0.3 is equivalent to 6.67 liters of HNO3. And that's our answer. All right, the next example. Pure acetic acid is a liquid with a density of 1.049 grams per milliliter at 250 Celsius. Sorry, not 250 Celsius. This is supposed to be 25 degrees Celsius. Calculate the molarity of a solution of acetic acid prepared by dissolving 10 mils of acetic acid at 25 degrees Celsius in enough water to make 100 mils of the solution. And acetic acid has a molecular weight of 60.1. So, let's see. Let's go back to this again. They want us to calculate molarity. Molarity is moles over liters. And we're taking 10 mils of acetic acid in enough water to make a 100 ml solution. And we have the density. So we're starting with 10 mils. I'm going to call acetic acid AA, so I don't have to write it out. So we've got 10 mils of AA. And we know that the density is 1.049 grams per 1 milliliter. So our milliliters are now going to cancel. We also know that 1 mole, because it's the GFM, is 60.1 grams. So our grams cancel. So when we do the math on this, we're going to get our moles, which is 0.175 moles, and we are making a 100 milliliter solution, so 100 milliliters is 0.1 liters. So that is going to be 1.75 molar acetic acid. So essentially, we are just continuing to use dimensional analysis to get from one set of units to another. All right, now we're going to take a look at something called dilution. Well, you guys all know what dilution is. It means basically to water something down. The definition would be a process of preparing a less concentrated solution from a more concentrated one by adding water. Well, a solvent. In the most cases, it's water. In the most cases, it's water. So what is our key idea? The biggest thing to remember is when a solvent is added, to a solution, the moles solute remain unchanged. So the formula is M1 or M initial times volume initial yields molarity final times volume final. Now, sometimes this formula is written as M1V1 equals M2V2. It's the same thing. Last year in titration, we used it as MAVA equals MBVB. So you can see that you're essentially using the same formula. But in dilution, you're taking the molarity and volume of one substance, you're adding water to it, and you're getting a new molarity and a new volume. So it could be written any of these ways. It essentially means the same thing. Okay, first example. An experiment requires 150 milliliters of a 2 molar HCl solution. All that is available in the laboratory is a 10 molar HCl solution. How do you prepare the required solution? So there's two steps to this, really. There's the mathematical step in which you have to know what you're going to need from the 10 molar stock solution, and then there's a way that you actually have to prepare it, the physical manner in which you prepare it. So let's go through the math portion first. So our final molarity, this is what we want. Our final molarity is 2 molar. So this is our MF. And our final volume is 150. And our initial molarity is a 10 molar HCl stock solution. So using the formula MIVI equals MFVF, we know that this is going to be 10. This is basically our X, and this is going to be 2 molar. And we talk about molarity. Molarity is moles per liter. So we really should be putting this in liters just so that we're consistent with our units. So this would be 0.150 liters. And when we solve for X, we get X equal to 0.030 liters, or technically what we're going to do is we are going to use a pipette, and we are going to draw out 30 milliliters of the 10 molar HCl solution. And we are going to put it in a 150 volumetric flask. And then we are going to add distilled water up to the mark. Okay, last slide. A couple of more examples. How many milliliters of a 0.250 molar solution would be required to prepare or do each of the following? So in A, we're going to use this 0.250 molar HCl solution to prepare 50 mils of a 0.1 molar HCl solution. So this is simply a dilution, okay? So we're using our MIVI equals MFVF. Our initial is 0.250 molar. We don't know the volume, but we know that we want to wind up with 0.1 molar. And if we put this in liters, that's going to be 0.050 liters. And when we do the math on this, X comes out to be 0.020 liters, or 20 milliliters. So we would use our pipette, draw out 20 milliliters of the 0.250 molar HCl solution, put it in a 50 milliliter volumetric flask, and then dilute it with distilled water up to the mark. In B, we want to react the 0.250 molar HCl with the OH in a barium hydroxide solution that is 0.2 molar, 15 mils. So basically I have 0.2 molar barium hydroxide, 15 mils, and I want to react that with the 0.250. So how many milliliters of that do I need? Well, technically, if we're doing this correctly, we should write a reaction. So I've got BaOH2 reacting with HCl, and that's producing BaCl2, and H2O. And then I would need a 2 here. That's balanced. No, maybe not. 2 H's there, 2 H's there, so that's 4 H's. Now we're balanced. Okay, so now I'm going to use plane stoichiometry, because right away I notice my H to OH ratio is not 1 to 1, which is what we usually need it to be in a neutralization reaction, because this is an acid and a base. So I'm going to start with what I'm given, and I'm given 15 mils of the BaOH2. So I've got 15 mils. Okay. And we know that the molarity is 0.2 moles per 1 liter. So I know that 1 liter is 1,000 milliliters. So I've got 0.2 moles per 1,000 milliliters. I want to get rid of that milliliters. Now, in my balanced equation, this is my moles of BaOH2. I have 1 BaOH2 going to 2 HCl, and that's moles of HCl. So this is moles, right? And this is moles, and that was moles of the BaOH2. So my moles cancel. And I'm not there yet, okay? I need milliliters. I also know that I have a 0.250 molar solution, which is moles per 1 liter, or 1,000 milliliters. So moles of HCl cancel, and I'm going to be left with milliliters of HCl. When I do the math on all this, I get 0.024 milliliters, or 24 liters, however I'm asked to report it. Okay, I'm going to try to squeeze in this last problem. Move this up a little. And I see some problems with this last one. When it opened, it didn't open right. So this should be a yield sign here. This is Ca plus 2 ion plus H2O plus CO2. Okay, and this is CaH plus ion. All right, so now we want to know how many milliliters of the 0.25 molar HCl is going to be required to dissolve 0.5 grams of CaCO3. So we know that we're going to start with what we're given in the problem, but we need a couple of things. We need the GFM of the CaCO3. So I'm just going to write that down here. That is going to be 100.0869 grams. Okay. We already have a reaction, so we can just start 0.500 grams of CaCO3, and we know that 1 mole is equal to 100.0869 grams. This is CaCO3. So our grams are going to cancel. And in our equation we have 1 CaCO3 moles, and we have 2 H plus, which is our HCl, so this cancels. Now we have moles. We need molarity. Go from moles, so our molarity is 0.250 moles. Remember, this is what's going to mess you up. Okay, you need to remember every time you see that it's 0.250 moles per 1 liter. You need to say it all the time. 0.250 moles per 1 liter or 1,000 milliliters, because they want to know milliliters. So my moles are going to cancel. So I've got 0.5 times 2 times 1,000 divided by 100.0869 times 0.25. And when I put all of that in my calculator, I get 39.96 milliliters, which is probably close enough to 40 milliliters of the HCl. Okay, and that's it. So I'll be looking for feedback on this recording method, if it's better than Camtasia or equivalent to.